Hey everyone, this is Mr. Heier. We're going to talk about collisions today. Very similar to the lab, that you all did last week. We're gonna utilize some of that information that you were able to see. All right. So, what is a collision? It's when two objects hit one another, and we typically say it happens over a very short amount of period of time. And so, when the two objects do collide, momentum is transferred or split up between the two objects, depending on if they're moving or if both are moving or if one's at rest. Right? Conservation of momentum, just like conservation of energy, is very important here. Conservation of momentum basically says that the momentum before the collision, the total momentum in the system before the collision, is going to equal the total momentum of the system after the collision. Right? And that's what this says here. Net momentum before equals the net momentum after. Right? And this is always true as long as there are no outside forces acting on the system. Okay. Now, typically when cars collide, there's friction and things like that. But as I said at the beginning, the collision is considered to be so short that those outside forces don't have a chance to have a factor. So we can apply conservation of momentum here. All right. So when two objects collide, when we're talking, the first type of collision we're going to talk about is the elastic collision. That's the first type of collision y'all did in the lab last week, right, when you set the elasticity equal to 1. All right, and when that happens, when the two objects collide, kinetic energy is conserved, meaning the kinetic energy stays the same. And as always, momentum stays the same. So when they hit, both of those things for the total kinetic energy and the total momentum stayed the same. Right? And so basically, the equation we use here is just basically the momentum of the first object before the collision plus the momentum of the second object before the collision equals the momentum of the first object after the collision plus the momentum of the second object after the collision. And if you, so basically, the total momentum before equals the total momentum after. You have to remember that this is a vector. So if they're in opposite directions, one of the velocities has to be positive and the other velocity is going to be negative. So let's look at some examples. All right, so a 0.17 kilogram cue ball is moving at 2 meters per second and hits the back of a 0.16 kilogram striped ball that is already moving at 0.7 meters per second. So they're both moving in the same direction here. It's just that the cue ball catches up to the striped ball. If after the collision, both objects separate and the cue ball is still moving forward at 0.4 meters per second, what's the velocity of the striped ball? So basically all we do here, we're going to again use conservation of momentum. 1 will be the cue ball, 2 will be the striped ball. And so we just put in the numbers. Oops. Let me get rid of that. There we go. All right, so we see here that mass of the cue ball times the initial velocity plus the mass of the striped ball plus its initial velocity is going to equal to the cue ball's mass plus its final velocity plus the striped ball's plus its final, or times its final. And that's the last thing that we have to calculate. All right, so if we plug the things into our calculator, we get these numbers, subtract over, and solve for V2 final. All right, so pretty straightforward. V2 final is 2.4 meters per second. What if they're going in opposite directions? So same type of problem, 0.5 kilogram croquet ball moving at 1.6 meters per second hits another croquet ball, so same mass, moving 1.0 meters per second in the opposite direction. So one of these is going to be positive velocity, the other one's going to be negative. Doesn't matter which one as long as you're consistent. Right? After the collision, the first croquet ball moves back with a velocity of 1.2. What is the velocity of the second ball? All right, so again, we use conservation of momentum for elastic collisions, right? So 0.5 times 1.6 plus 0.5 times -1 because it's in the opposite direction. And then the final velocity of the first ball, since it went backwards, is also going to be negative. So 0.5 times -1.2. And we solve for V2 final. Plug the numbers in our calculator. Subtract, move things together to isolate V2 final, and we get a final answer of 1.8 meters per second. And that would be in the opposite direction that it was moving, I guess to the right, if you want to say that. All right, next type of collision we'll talk about are inelastic collisions. And in an inelastic collision, kinetic energy is lost, right? And typically what happens is that they remain attached. They hit together and then they stick. All right, so this actually makes calculating it a little bit easier because if they stick together, they have the same final velocity at the end, so we can just add their two masses together. It's the same equation. This is just m1 v1 final plus m2 v2 final. But v1 final and v2 final are the same, so we can just call them v final, and so we just can write it like that. All right, so 3,000 kilogram car moving at 50 meters per second, rear ends a 2,000 kilogram car moving at 35 meters per second. So it says rear end, so they're both moving in the same direction, so they both have positive velocity. If the bumpers of the car become attached in the collision, so they stick together, what's the final velocity of the cars together? Right, so again, we use our equation. So 3,000 times 50 plus 2,000 times 35, again, same direction, so both velocities are positive, equals the total mass, which would be 5,000 times V final. Plug the numbers in the calculator, and we solve for V final, which is 44.5 or 44 meters per second. Right. And then, what if it was a head-on collision? Then then one of the velocities would be negative. So same problem, but the difference would be that this velocity here is negative. And notice that your answer is going to be completely different. Much slower after they hit together. Right? And here's one where a car is at rest. So a 1,000 kilogram car hits a 2,000 kilogram car that's at rest. 1,000 kilogram car has initial velocity of 40. What's the final velocity? Right? So basically, if this velocity here is 0, then this part goes away. Right? So 1,000 times 40 plus 0. And then we can calculate our final velocity of 13.3 meters per second. All right, go ahead and try it, pause it, and make sure that you get the right answer. All right, finally, there's one last type of problem. It's a kind of recoil type of situation, like when you fire a cannon. If you've ever seen a cannon fired, cannonball goes one way and the cannon itself goes the other. Okay, so they start together and then they separate. Right? The initial momentum typically is 0 because everything's at rest. Right, so we would just say 0 is equal to m1 v1 final plus m2 v2 final. It's kind of the reverse of an inelastic collision. And we'll just do one quick example. 510 kilogram cannon with the cannonball inside, so it's 510 total. Fires a 10 kilogram cannonball with the speed of 200 meters per second relative to the muzzle. Cannon is on wheels and can roll. So what speed does it recoil? Right, and so basically, it's the same thing, except we said this whole thing initially is going to be 0. Right, so 0 equals m1 v1 final plus m2 v2 final. V1 can be the cannon, v2 can be the cannonball. Right, so the mass of the cannon and the cannonball is 510. So without the cannonball, it would be, so we can say here that m1 is 510 times v1 final plus 10 times 200. And we just solve for the velocity of the cannon, which is negative 3.92 meters per second. It just means it goes in the opposite direction of the cannonball. That makes sense, everybody? Notice that the cannonball moves a lot. The cannon moves a lot slower than the cannonball because the cannon has a lot more mass than the cannonball does. If they were closer in mass, then the cannon would move faster. All right, so practice some of these problems that you've gotten. We'll go over a couple of them in class tomorrow, and we'll see where we go from there. Remember that our test is on Friday, so make sure that you can do these before Friday. Well, have a great day.